the session, right. So, in the last session we were discussing about the Routh Hurwitz criteria and we were observing the certain example, and then we had observed the condition of auxiliary equation, how we can obtain the auxiliary equation. It means whenever our two rows or you can say complete rows is 0, after that we need to choose the auxiliary equation so that we can continue the Routh Hurwitz table, right. So, this table or you can say this equation, you can say auxiliary equation, it is symmetric in nature, right. So, we discussed this thing in the last session. So, in today's session we will discuss one more example of Routh Hurwitz criteria, then we will discuss about the conditionally stable system, then we will discuss about the drawback of Routh Hurwitz, and then we will see the introduction to the root locus. So, auxiliary equation that I already told you, whenever you solve this auxiliary equation you will always get a symmetric root, just like here. So, this symmetric root may lie on the real axis or it may lie on the imaginary axis, right. So, here you can see this symmetric root may lie on the imaginary axis, or you may get here complex conjugate roots in case of auxiliary equations, right. So, this slide we had seen in the previous lecture. So, now one more example we would like to solve using Routh Hurwitz criteria. So, this is the quadratic equation given to us, right. So, here we can observe highest power is 5. So, I have to arrange my first column like this. So, S5 will be the first parameter, second would be the even power. So, I have to complete the first row and second row. In the first row I have to start from here. So, this is the coefficient 1. Now, next odd is here 2, coefficient is 2, next odd term is here S, coefficient is 1, right. In the same way when we go for even, so I will start from S raised to the power 4, coefficient is 2, right. Then next even power is S square, coefficient is 4, then next even power we can say it is 2. So, this would be a 2, right. So, this first two row we can easily complete. Now, we will proceed to the next step. So, I will start from this 2 multiplied by 2, it is 4, minus of 1 cross 4, right. So, this will gives me 0, divide by 2, it means this element would be 0. In the same way, if I like to fill the second element, I will multiply 2 with 1 minus 1 will multiply with the 2, 2 minus 2 is 0, divide by 2 will again gives me 0, right, and this term would be 0 because there is no other term present there. So, my third row is coming complete 0, right. So, this situation we had observed in the previous case. So, I need to choose here auxiliary equation. So, basically I have to choose a even power equation, right. So, whenever we have to write the auxiliary equation we have to choose the even power. So, what would be my equation? It is 2 s to the power 4 plus 4 s square plus 2 equal to 0, right. So, this equation will come whenever we choose auxiliary equation from even power, right. So, this auxiliary equation given by this equation that I told you. If you further simplify it, you can take 2 common s to the power 4, it will become 2 s square plus 1 equal to 0. So, we will get this equation, right. So, now to determine the our next element we have to differentiate this auxiliary equation with respect to s, and we will get these two element 4 s cube plus 4. It means our new element would be 4 and 4. So, here you can see again 4 is again common to both the term, you can make it 1 1 or you can continue with 4 and 4, right. So, it does not impact. So, here I will go for 1 1, I have to simplify it. So, my new element, sorry, this is my new element 1 1, okay, and then I have to continue my Routh Hurwitz table. So, again if this new element I have to create this new entry. So, 1 multiplied by 4 minus 2 divided by 1, right. So, this will gives me around the value 2, okay, and if you see this one, this entry 1 you can say 1 multiplied by 2, right, and minus you can say 2 multiplied by 0 and divide by 1, this will gives me 2. So, again I am getting here 2 and 2, right. So, again you can see this 2 and 2 is coming whenever I have to further solve it, okay, this entry should be 2 and 2 instead of 1, right. So, whenever I have to complete the next row, again 2 multiplied by 1 minus 1 multiplied by this term, okay. So, this will gives me 0 again, you can say 2 multiplied by 1 minus this 1 multiplied by 2 divide by you can say 1, this term again comes 0. So, I am writing 0 here. Now, again if I look, this 2 is multiplied by 0 here and this 1 is multiplied by 0. So, again numerator part is 0. So, I will get 0 again. So, again this is a special case where after substituting the auxiliary equation element, we are getting again 0 or complete 0 row, right. So, again to replace it, again we have to follow this auxiliary equation. So, I need to choose this power of, you can say, even power. So, I will write this equation as 2 s square plus 2 equal to 0. 2 is common to both, I can make it as s square plus 1 equal to 0, right. And here to determine this new element, I need to differentiate this equation, right. So, this is my auxiliary equation. Now, I have to differentiate it with respect to s and I will get 2 s plus 0. It means my new element is 2 and second element is 0, and then I will continue my table. Okay. So, after that, after solving 2 multiplied by 1, 1 multiplied by 0 divided by 2 will gives me 1. So, this is the simplified Routh Hurwitz. So, what we had found in this case, we are getting 2 complete 0 row, right. What it means, we need to use 2 times auxiliary equation. Okay. So, it means we are getting here 2 auxiliary equation. So, one auxiliary equation will give us 2 symmetric root. If second auxiliary equation is coming, it means it will again give us 2 symmetric root. If I plus both the roots, total 4 roots are coming because of these 2 complete 0 rows. Okay. So, we can see, so we are getting here the repeated roots on the imaginary axis, right. So, here when we see plus j minus j plus j minus j, if we solve this auxiliary equation, if I solve it, so I will get the 2 auxiliary term, one is plus j and minus j, and before that if we were solving the above equation, then again we will find plus j and minus j. It means what is happening, we were getting the 2 repeated roots on the imaginary axis. So, now we have to check what stability of the system, whether it is stable or not. So, I have to observe my first column, it is completely positive. So, I told you that in the previous lecture, whenever complete row is 0, then our system is not stable. So, there is 2 condition, one, it may be marginally stable or it may be unstable. So, here I need to check the condition whether my system is marginally stable or it is unstable. So, here I am getting the 2 auxiliary equation and 2 repeated roots at plus j and minus j. If 2 roots are repeating on the imaginary axis, so we had seen in the previous lecture, we will get here an unbounded response like this, right. So, this will come whenever I am getting the repeated roots on the imaginary axis. So, this will makes my system unstable. Okay. So, this is the one example of unstable system. You can see your all column is positive, but you are getting the repeated roots on the imaginary axis. So, it is unstable. So, in short, whenever you are getting your rows complete 0 2 times, so directly you can write your system would be unstable. So, you have to check what is the location of auxiliary roots. If it is on imaginary axis and they are repeating, it means this is giving us the condition of instability. Okay. So, in summary, if we whatever we had seen, if 0 is coming in the first column of the Routh Hurwitz table, then at least single root is lying on the RHS of S plane. So, it will make system unstable, right. This is the one thing that we had seen, and if row of 0 occur in the RHS table, it shows the symmetric roots are present on the S plane with respect to origin, right. So, whether it is lying in real axis or imaginary axis, we have to check. If these roots lying on the real axis, it means my system would be unstable. If it is lying on the imaginary axis, it means our system may be marginally stable or may be unstable. Okay. So, this thing we have to check, and you can say whenever I am getting symmetric roots on real that I told you, so it means one root lying in the RHS. So, directly we can say our system is stable, and if we are getting repeating roots on the imaginary axis, then this would be unstable system. Okay. So, this is about the theory of auxiliary roots that I told you, nothing new is here. Okay. So, whenever we would like to solve the auxiliary roots, okay, then we can suppose this is the equation b s square plus d is coming from Routh table, it is coming from RH table. Whenever our one row is complete 0, then we will get this type of equation auxiliary roots. Okay. So, when we like to solve the value of this s, so we are getting s square equal to minus d by a and s equal to plus minus j under root d by a, and s is a complex term sigma plus j omega. So, from here I can calculate the frequency of oscillation, right, where that you can say it is under root of d by a. So, whenever auxiliary roots are coming and they are lying on the imaginary axis, it means my system would be what? Marginally stable. If single roots are lying, it means there would be certain sinusoidal response at the output, and that output will have certain frequency, that is omega. So, this is the way that I can calculate the frequency of oscillation in case of marginally stable state. Okay. So, here we have to take out the root of auxiliary equation. Basically, we have to choose of power 2, from there we will get the value of frequency. So, it will help in most of the numerical, whenever we are solving the numerical in Routh Hurwitz and we would like to know what is the frequency of oscillation. So, we have to choose a complete 0 in RH table, then select auxiliary equation, then solve it, determine the root, and root will tells you the frequency parameter, that is omega. Okay. So, I hope this concept is clear to you. Now, we are switching to the next condition or next state, that is conditionally stable system. So, in this case what we can observe, our Routh Hurwitz criteria will explain conditionally stable system. It means it is stable for certain range and it is unstable for certain range of k. Okay. So, here k is a basic parameter which will decide the stability of the system. It means if we are writing the characteristic equation and we are getting the k terms in the characteristic equation, right, then the finite value of k will give you the stable condition and finite value of k will gives you unstable condition. So, for which value of k your system is stable, it will explain by conditionally stable system. So, for that purpose I am assuming that this is my input Cs and Rs is coming at the output, and this is my GSHS, which is k is the DC gain of the system. So, if I would like to write the Routh Hurwitz criteria or Routh Hurwitz table, I have to write the 1 plus GSHS equation. Okay. So, when I write the 1 plus GSHS equal to 0, so k term will come in the picture, right, and this k will decide whether my system is stable or not. Okay. So, basically you can see I have to write 1 plus GSHS equal to 0, and then I have to write this expression. After solving, it will come like this, after solving it will be like this. So, my question is for which value of k my system would be stable, or for what range of k my system is stable. So, I have to go for Routh Hurwitz table again. Okay. So, I have to write this equation, arrange, because maximum power is s cube, s square, s1, s naught in the decreasing order. Then odd power is s cube, coefficient is 1, next odd power is s1, coefficient is 30. Now, come to s square, this row, second row, coefficient is 13, next even power is k. Now, after solving you are getting 13 multiplied by 30 minus 1 multiplied by k divided by 13, this equation will come. After solving it you will get what? This term multiplied by k, you can say this term will multiplied by k, and 13 multiplied by 0 divided by this term will gives you k again. So, you can check k is the last term, k is coming here, it means my Routh table is correct here, right. So, now what is my main aim? That my first column should be positive for stable condition, right. If I want to say my system is stable, it means my first column should have positive sign. So, here this one having positive sign, 13 is positive sign, but this is positive or not I do not know, but for stable it should be positive. This is positive or not I do not know, but if this system has to be stable, this k should be positive. If k is positive, then I can say here k is greater than 0, right. So, this is my first condition, first range of k. In the same way, this term has to be positive. If it has to be positive, so this value should be greater than 0. So, if I put this condition, if I solve it, so I am getting what? K is less than 390. So, I am getting here the two range of k. Whenever my k is greater than 0 and less than 390, so we can say our system is stable. Okay. So, you can say what we need to check here, the first column element, it should be positive for stable condition. Okay. So, that is why our range is coming k greater than 0 from here, and second term, this term is also should be positive greater than 0, and it is giving this condition. If I combine both the condition, so this is the range of k for which my system is stable. If I increase value of k beyond 390, then my system would be unstable. Okay. So, when we study about the Routh Hurwitz criteria, then this thing will be more clear to us, right. So, here one shortcut is here. Suppose this equation is given to us and the order of equation is 3. This is basically a quadratic equation, right. So, if I directly want to know whether my system is stable or not without going to the table, only to verify my answer. So, what I will do? I will assume the coefficient of this S cube is A, it is coefficient of S square is B, coefficient of S is C, coefficient of this S raised to the power 0 is D, right. So, I will write this condition whether B C is greater than A D. So, separately I will calculate B C and A D, I will calculate their product. So, here A is equal to 1, B is equal to 13, C is equal to 30, D is equal to K. So, I need to calculate these two product, okay. And if I know my system is stable, so for stability B dot C should be greater than A dot D. So, here B is 13, C is 30, it should be greater than A is 1 and D is K, right. So, here what we are getting 13.3, it means 390 greater than K, or you can say one condition is coming K less than 390. So, it is valid whenever we are having the power of 3, you can say maximum power f of S in quadratic equation is 3, then we can obtain this condition, right. So, in the same way we can say this K has to be positive if my system is stable. So, one condition is K greater than 0 and second condition is K is less than 390. So, one way to verify your answer whenever S cube is the highest power in quadratic equation. So, this is the alternate method. So, for exam you have to follow this method, this will give you marks. The next step is only for verify your answer. Okay. So, this step should not be followed, and if you are getting the marginally stable condition, so you will find B C is equal to A D, and whenever your system is unstable you will find B C is less than A D. So, you can try and verify your answer, right. Now, what is the drawback of Routh Hurwitz criteria? So, Routh Hurwitz criteria basically gives you the absolute stability. It will tells you whether the system is stable or not in terms of yes and no, right. So, it whenever it is stable, it will say yes because certain roots lying in the right half system is unstable, and if all the poles lying in the left half, it will say my system is stable. So, the concept of relative stability, how much it is stable, for which value of gain, for which value of range my system is stable, this information is missing in case of Routh Hurwitz criteria. So, this is the one drawback. Okay. So, you can say here we had seen the conditional stability where K was a factor. So, if we vary K from minus infinity to plus infinity, so for which value it is stable, for which value it is not stable. So, this is not clearly defined here. Okay. So, you can say the Routh Hurwitz criteria does not tell about the amount of overshoot, settling time, system response with respect to the open loop system. So, this thing is missing, and you can say relative stability, if my system is stable, for which values of K, for which range of K it is stable, this you can say this type of information is a little bit missing from this Routh Hurwitz criteria. So, when we discuss about the other criteria, just like you can say gain margin and phase margin, then we will came to know the importance of relative stability. So, relative stability can't be explained by the Routh Hurwitz criteria. Okay. So, now our next topic is here root locus. So, to overcome those limitations of Routh Hurwitz criteria, we are going for root locus, right. So, here in the root locus we will observe that we can a little bit calculate the relative stability, right. So, how much my system is stable exactly we can know from the root locus. So, what is root locus we will see first. The first term is root, second term is here locus. So, what is root? So, this root is basically roots of quadratic equation. So, I will write quadratic equation as 1 plus GSHS, whenever GS is basically a transfer function, HS is the feedback element. So, if I take the root of this equation, then this will gives me the value of closed loop pole, and we can say it will represent the closed loop transfer function, right. So, and if we come for locus, so you know that locus is basically a path or graphical representation, right. So, whenever I graphically represent the root of quadratic equation, then I will obtain a graph which is known as root locus. Okay. It means we need to get the quadratic equation in terms of k, right, and then we need to determine the root of quadratic equation, right, and we will get a certain locus or graph, and this graph is known as here root locus. Or we can say what is root locus? It is a graphical representation of roots of quadratic equation. It is path of closed loop pole that you can say, or it is graphical representation of closed loop poles or roots of quadratic equation as gain parameter k varied from 0 to infinity. So, in next slide we will see what is happening in the root locus. In the root locus we need to plot various roots of quadratic equation for different value of k. So, we are varying the k from 0 to infinite, and then we are observing the location of roots, and then we are making a graph, and this graph is basically the root locus. Okay. So, in the root locus we vary value of k from k equal to 0 to k equal to infinity, and we observe the variation in the closed loop poles location, right. So, whenever we are dealing with the quadratic equation, it means we are dealing with the closed loop pole directly. So, when I vary the value of k from 0 to infinity, it means what we are doing, we are varying the location of closed loop poles, right. So, or we can say the closed loop pole varies with different value of k and forms a path, and this path is known as root locus. So, root locus always start from k equal to 0 and terminate at k equal to infinity. Okay. So, the locus we can say here, the locus of migration of root of quadratic equation in the S plane is called root locus. This is the alternate definition, and this root locus technique was introduced by W.R. Evans in 1948, and it is a graphical method for sketching the locus of roots of the quadratic equation in the S plane as design parameter of the corresponding system is varied. So, as we varied the value of k, different roots will come, and basically they are the location of closed loop pole, and if you join all the closed loop pole location, you will get a graph, and this graph is here root locus. So, to understand it, we have to go for angle and magnitude condition. So, I will explain angle and magnitude in the next lecture about it. Okay. So, first we would like to see about the basics of this root locus. So, here my GS is given like this, okay, and the quadratic equation is given like this, 1 plus GSHS is equal to 0. So, here this is my open loop transfer function. By applying a feedback, it will convert into a closed loop transfer function, where CS is my input and RS is my output. Okay. So, here my quadratic equation is 1 plus GSHS is equal to 0. If I solve it, I will get this equation. So, here I will choose case 1 when k is equal to 0. Then what about the closed loop pole? So, when k is equal to 0, you will get this equation. After solving, you are getting these two roots. So, for k equal to 0, I am getting the 2 pole at minus 2, 1 pole at origin, 0 and minus 2. In the same way, when I change the value of k to 1 by 2, then my equation will become like this. After solving, I am getting the equation, you can say s equal to you can say minus 1 plus 0.7, and these two roots are coming. So, here minus 1.7 is coming, and second root is here minus 0.293 is coming here. Okay. In the same way, when I put here k equal to 1 in the above equation, this will become my quadratic equation. My new roots are minus 1 and minus 1. So, here two roots are repeating on the real axis. For case 4, when I put k equal to 2, so I am getting this pole location minus 1 plus j. So, this 1 plus j location is coming, whenever I vary the value of k. Okay. So, these are the basic closed loop poles for different value of k. Okay. So, these 4 k's we will discuss in the next lecture to understand the concept of root locus. Okay. So, thank you for today.